So, in this video lecture, we will look at some of the shortcomings of the capacitor model proposed by Helmholtz equation, right? And we will also look at the importance of looking at incorporating other aspects, right? So that the results that we get is pretty accurate, right? So in this video lecture we will also look at Gouy-Chapman electrical double layer model, which is improved version of the electrical double layer model. Okay, so we will look at the shortcomings first, and then we will see the Gouy-Chapman model, right, in this video lecture. Okay, let's begin. Yeah, so as we have just now described, you know that the limitations of capacitor plate model, which was proposed by Helmholtz in 1879, right, are listed here. Okay, so the first and foremost shortcoming that if you want to present is the parallel plate assumption, right? So if you look at, there are two parallel plate, right? We considered both plate carries with it equal and opposite charge, right? With it, okay. Now the problem here is one of the plate is solid and rigid plate, okay, and the other one is the electrolyte, right? So we consider the strongly bound counter ions as the rigid solid boundary itself, which is actually not very accurate, okay, and the consequence of that will be one hand you will not get very accurate results. On the other hand, it also leave aside the dependency of electrolyte concentration, right, which is very much crucial, right. So because as you know, when when the electrolyte concentration goes up, when the strength of the electrolyte concentration goes up, it affects the distribution of the ions. So the counter ions and co-ions present in the solution also vary as a function of concentration, but these details are not presented by this model, that is the capacitor model. Okay, so that is actually a major drawback. And the other drawback is, so we considered parallel plate assumption, right? What if we have to deal with a situation where instead of parallel plate we encounter cylindrical shape, right, or spherical shape or any arbitrary shape? For such situation, this model does not provide any accurate results, because it considers basically parallel plate assumptions, right, which is not true always in all cases. So that is the another drawback of the model. The last but not least is that it actually ignored the the thermal motion of the ions. So you know that in the solution, due to bombardment of solvent ions, there will be thermal motion, right, because of the thermal energy, right, which is nothing but kBT. Okay, but because there will be thermal motion, ions will not be distributed uh, you know uh, in a linear in a linear fashion. Okay, it can be distributed in a random fashion. So that aspects not covered by the model. So we are going to look at, so these are the shortcomings. Now as a remedy to this, Gouy and Chapman have proposed another electrical double layer model. Okay, and that actually kind of incorporates or addresses these shortcomings or gaps. Okay, we will see them in detail. So this is nothing but the diffuse double layer, because it considers the diffuse double layer, right, and it is predicted by the proposed by the Gouy and Chapman, right. That's why it is called Gouy-Chapman model. Okay, and because it considers diffuse double layer, it means that they take the thermal motion of ions near the charged surface into consideration. That is very uh, you know uh, you know a very good thing considering the situation, realistic situation. And the next one is that um, in the capacitor model, unlike the capacitor model, here in the solution you also consider both counter ions which are attracted by the the charged surface, and the co-ions which are repelled by the surface. So both counter ions and co-ions coexist in the solution, which is also considered by this model. Okay. So remember, when we talked about the electrical double layer theory in the beginning, we said whenever you introduce a charged surface into the solution, you can expect three possibilities, right? One is strongly bound counter ion, weakly bound counter ion, diffuse counter ions. You may be asking, like, why these aspects are not taken into consideration in the first place itself. Remember, one would not get this much clarity in the first place itself, right? As we understand about the difficulties, okay, as we face the challenges, we try to ask questions and get answer. So with the time, we get more clarity, and with the time, we evolve, right? That's how these different models, came into existence. Okay, you may be wondering why in the Helmholtz model itself, this diffuse double layer thing was not incorporated, because at that time this much clarity was not provided. That's why this was not included. With the time, we understand better and we also evolved, right? So that's why different at different point of time you get different model. Okay, come into existence. Okay, so this particular model, remember, we just now described that there are three types of counter ions that we always encounter. One is strongly bound. So the capacitor model considered only the strongly bound counter ions, whereas the weakly bound and diffuse bound layer was not considered. So this Gui-Chapman model, Gui and Chapman, they consider not only the strongly bound, they also consider the diffuse double layer. Okay, so if you incorporate along with the parallel plate, if you incorporate this diffuse double layer, that means it is Gui-Chapman model. Okay, right. So the variation of the potential with the distance from a charged surface of, so now we are going to talk about any arbitrary shape. We are not only going to deal with the parallel plate. For any arbitrary shape, we know from a classical electrostatic problem, there is something called Poisson equation, which describes the variation of potential with the distance, right? So this is going to be our starting point. Okay, and so psi here is the potential, right? uh, and you can see that the variation of potential is described in all three coordinates. The rho star is nothing but charge density per unit volume. When you take into consideration in the region of space of your interest, if you include the total volume, then you will get the potential for the total charge, right, for a given problem. Okay, and you can also see in denominator we actually considered not just vacuum, which is E naught, we considered E naught into ER. So when I say E naught into ER, this is simply nothing but EM. Okay, um, so we take the advantage of the relative permittivity, which doesn't have any dimension unit. Okay, whereas the E naught is vacuum permittivity. So for different materials, we have already listed what is ER. So if you simply multiply ER with the E naught, what you will be getting is the EM, which is the permittivity of the any given material, right? Or medium, sorry, medium in this case, right? So since we are dealing with electrolyte, we have to include the medium, right? That's why we have taken E naught ER instead of just E naught. Okay. Yeah. So here we will try to obtain the potential variation across the surface, right, across the interface, right. So, as a function of distance as well as a function of electrolyte concentration. Okay. Our starting point is going to be the Poisson equation. Our first step will be to incorporate the the random distribution of ions, a function that will describe the random distribution of ions, right. And then we have to get the equation of psi, right, equation for psi as a function of distance as well as the electrolyte concentration, right. So, that is exactly what we are going to look at. Okay, right. So, our first step will be the Poisson distribution equation, right. So, we have written that here. So, when we say that we are talking about the diffuse nature of ions, right. So, thermal diffusion, and the distribution of ion will be random. Okay. Let us say we have a surface, right. Okay. So, what is the probability that any ions will exist? It could be counter ion or co-ion will exist. Okay. Here is that needs to be specified using a function, right. So, we are going to borrow this random the distribution of ion, which is a random which is a function in a random fashion. So, then we are going to incorporate. So, we are going to look at what is known as the Boltzmann distribution function. Okay. We are going to borrow this from the Boltzmann distribution function. Okay. And then we are going to use this in our equation here, plug it here, and then get the relevant the equation as a function of x and the electrolyte concentration. So, what this Boltzmann distribution function says is that the number of ions which can be defined as at Ni infinity okay. So, Ni infinity exponential minus Z I E psi, right, which is into kBt, right. So, this is our equation. Okay. What it says is that this Ni infinity is the concentration, the bulk concentration, right. This is bulk concentration. Okay. And whereas this one, so here this Zi is nothing but valence, and E is the electron, which the electron constant in terms of Coulomb, and then psi is the potential. So, Zi and E is nothing but Coulomb, okay, right, and psi is potential. Potential we can express as volt, right. So, Coulomb is equal to joule per volt, that we know. So, volt meaning joule per Coulomb, right, and this will be joule per, this is also joule, right. Okay. So, you will finally have dimensionless, right. This part will be dimensionless, and so we are talking about the number of ion distribution. So, what it describe is that when far away from the surface, which is bulk concentration we are talking about, far away from the surface, psi will be 0 because it will not have any influence. So, which means that when you move far away from the surface, psi will be no longer valid, psi will be 0. In such case, this exponential term will be 1, and you will be nothing, you will have Ni as Ni infinity itself. Okay. But as you come as you move towards the surface, right, when you approach when you move close to the surface, psi will be not 0, psi will be varying, right, as a function of distance. So, then you will have you will have this function will be like exponential decay. For example, if I have to specify this as a function of distance, right, distance as Ni, this will be varying something like this. Okay. So, this one is Ni infinity, right, this is exponential decay, and this part will be the potential correspond to this part will be psi naught, which is the psi surface potential of the surface itself, right. So, this is how the function will reflect, okay, when you incorporate the Boltzmann distribution function, right. So, what is rho star here? So, rho star is going to be N I Z I and E, right. So, this is our the definition, right, description for rho star. Now, you have to substitute this rho star here back into this equation. When you substitute, you will have del square psi is nothing but minus, so rho star by E naught E r, which is nothing but N I Z I E divided by E naught E r, right. So, what is Ni, which we described as Ni is nothing but Ni infinity exponential, okay, minus Zi E psi divided by kBt. So, this is what we described already, okay, multiplied by you will have Zi E, okay, divided by E naught and E r. So, this is what we have. So, we can actually use this equation as it is. So, del square psi, so you can express this. So, we can actually use the power series, right. So, let us say we have what is known as the d by Huckel approximation, okay, d by Huckel approximation, okay. What it says is that at a very low potential, especially when Zi E psi term is very less than kBt, then you can use this power series. So, you can expand like exponential minus x can be expanded as 1 minus x plus x square and so on, right. So, this is what we are going to use in this case as well. So, in such case, if I have to expand this, so del square psi will be minus, okay, this will be summation I N I infinity, this will be 1 minus Zi E psi divided by kBt, and then you have outside Zi E, right, divided by you have E naught E r, okay. So, this if I expand, I will have Ni infinity Zi E minus summation I, okay, Ni infinity Zi Zi square E square psi by kBt divided by E naught E r, okay. So, this is what exactly we will have. So, remember when I expand this Ni infinity Zi E will be 0, because when you expand you will have for symmetric electrolyte, we are talking about symmetrical electrolyte. So, our assumption is for symmetrical electrolyte like NaCl, okay, like NaCl, you can say that there will be equal number of distribution, right. For example, ZNa will be positive and ZCl will be negative, okay. In such case, you will have equal magnitude, but opposite in sign, right. So, all will get cancelled with each other. This will be almost, this will be like equal, I mean this will be equal to 0, okay, which also satisfies the electroneutrality condition, right. So, this term will no longer exist. Now, we will only have this term, which means that we will have del square psi is nothing but, okay, you will have minus minus plus, then you will have Ni infinity, okay, and Ni infinity Zi square E square, okay, psi, okay, divided by kBt E naught E r. So, this is what we will have, okay. Now, you can call this all this constant term as k square, which is nothing but d by Huckel parameter, okay. This is nothing but d by Huckel parameter. So, if you just incorporate this as del square as k square psi, okay. Now, you have to just expand this equation So if you solve this equation, okay, you will be getting psi as a e power kx plus b e power minus kx. Okay. So if you use this boundary condition, that is x tends to 0, psi tends to psi naught, and x tends to infinity, psi tends to 0. Okay. And so if you expand this del square psi equal to k square psi, uh, right, if you try to solve for psi, you will get this auxiliary equation, right. And if you substitute this two boundary condition, that is x tends to 0, psi tends to infinity, which means that in first instance you will get a plus b equal to psi naught. In second, when you apply second boundary condition, you will get a equal to 0, right. Ultimately you will have b as b will be psi naught, right. So if you use this two boundary condition, okay, you will get psi as psi naught e power minus kx. Okay, this is our equation. If you refer to this equation, you will see that psi is expressed, okay, psi is expressed as a function of x, and the remember k is the Debye-Hückel parameter, which is actually a function of concentration Ni infinity. Okay. So if the concentration of salt or electrolyte goes up, this will change. So this equation is dependent on distance as well as the concentration, the electrolyte concentration. Okay. And that's how the Gouy-Chapman model has been proposed, by assuming that by following certain assumptions like Debye-Hückel approximation is valid, symmetrical electrolyte. By making these two assumptions, you can express this model, Gouy-Chapman model, okay, as a function of x, that is distance, as well as the electrolyte concentration. Okay, this is represented. Electrolyte concentration is explicitly mentioned in the equation, that is Debye-Hückel parameter itself, right? Yeah, so there is some correction over here. So here we have obtained the equation as a function of distance and electrolyte concentration. For this problem, we have chosen one dimensional equation, right. So we have only considered that only this variation of psi in the x direction is considered. Okay, and rest of the coordinates were ignored. So that's how this equation has been derived. Okay, just keep in just note, just keep it noted that we have obtained this equation by assuming that the problem is applicable in one dimension only. Okay. Yeah, so similarly for spherical geometry as well as cylindrical geometry, one can obtain the function, right, equation of psi as a function of the radial distance, right, as well as the electrolyte concentration, okay, as given here, right. So so one can use the Boltzmann distribution equation, and then try to solve for various geometry using the approach shown here. Uh, for example, for spherical geometry, how you can get the psi as a function of the distance as well as the electrolyte concentration. Similar way for cylindrical surface, how one can get the the surface potential as a function of distance as well as electrolyte concentration can be obtained using this approach shown here. We will stop here. We will continue from the next lecture. Thank you.